I've divided section 8.2 into two videos. This part 1 will just be algebra, showing you what rational functions and partial fractions are. So a rational function, first we need to define it, of course. It is the quotient of two polynomials. For example, 3x squared plus 1 over x cubed plus x plus 3. That's an example of a rational function, the quotient of two polynomials. I'll often refer to them as n of x over d of x, numerator polynomial over denominator polynomial. Now, if there's any questions in your mind about what is a polynomial, I suggest that you Google it and find out. Polynomials only have natural numbers for their exponents on x. So be sure and know exactly what a polynomial is. Now, a proper rational function is a rational function, the quotient of two polynomials, but being proper means that the degree of the numerator polynomial is strictly less than the degree of the denominator polynomial. And that's going to be very important in our integration, is that we only use this method that we're going to describe on proper rational functions. Here's two examples of rational functions that are not proper. Notice the first example here is x squared over 1 plus x squared. The degree of the numerator is 2 and the degree of the denominator polynomial is also 2. So it is not proper, and it can be written this way. And I'll show you how to do that in a second. We'll divide the denominator into the numerator, and we will get a quotient of 1 minus 1 over 1 plus x squared. So notice we've written this rational function that was not proper as a little, well, it's just a constant, but it's also a polynomial of degree 0, plus another rational function that is proper. Similarly, in this example, we have the degree of the numerator. The degree of the numerator polynomial is the highest exponent on x, so that is 3. And the degree of the denominator is 2. And therefore it is not proper. And if I divide this denominator into the numerator, I would get a polynomial x plus 1. This is a polynomial plus x minus 2 over that denominator, x squared plus x plus 1. A little polynomial plus a proper rational function. So let me show you how to do this. We see this example, we have the degree of the numerator is 3, the degree of the denominator is 2, so this rational function is not proper. So I'm going to divide the denominator into the numerator. Let me just show you something that is similar to it. In the rational numbers, we might have the number 7/2. If I take 2 and divide it into 7, I get 3 and 6 with a remainder of 1. So I could write 7/2 as the quotient 3 plus the remainder 1 over the divisor 2. And actually, you can just remember this simple little thing that everyone knows to recall how to do this if you forget. Alright, so let me show you what we'll do. We take x squared plus x plus 1, and we're going to divide it into, just like we divided the 2 into the 7, x cubed plus 2x squared plus 3x minus 1. Now when you do this, you only have to look at the term with the highest power of x. That's the only one that you'll be dividing with. So you take x squared goes into x cubed, x times. Whoops, I meant to stay in yellow. And x, now I multiply x times this whole polynomial here, the divisor. So x times x squared is x cubed, plus x times x is plus x squared, plus x times 1 is plus x. And now I'm going to draw a line like this under everything, and I'm going to subtract. So you might want to just go through and change the sign of everything and then add, or you can just remember and subtract. I change the sign and now I add. So the x cubed and the minus x cubed cancel, and I have 2x squared minus x squared is x squared. 3x minus x is plus 2x, and I have the minus 1. Now I divide again. X squared goes into x squared once, plus 1. And I multiply. 1 times x squared is x squared, plus 1 times x is x, plus 1. And again, I'm going to subtract. Go over here, and again, I will change the sign. If it was a minus, I change it to a plus, and then add. So the x squareds go away, they cancel, and I have 2x minus x is x, and minus 1 is minus 2. Now notice, as soon as I get to a remainder that is of lower degree than the divisor, here we have the degree of the remainder is 1 and the degree of the divisor was 2, we're done. And now all we want to do is express our result. So how do we write this? Well, remember over here at the 7/2 we got 3 with a remainder of 1, so it was 3 plus the remainder over the divisor. It's the same thing here. I'll write that rational function is equal to our quotient x plus 1 plus the remainder x minus 2 over the divisor x squared plus x plus 1. So we have written this improper rational function as the sum of, well, I don't need these parentheses, but the sum of a little polynomial plus a proper rational function, degree 1 on the top, degree 2 on the bottom. And so you'll need to know how to do that when we start using the method of partial fractions for integration, because they only work with proper rational functions. So this is a fact. In fact, it's really a major theorem in algebra, that every polynomial can be factored into a product of linear and or irreducible quadratic factors. So let's make sure we know what each of those words mean. A linear factor is of the form ax plus b. In other words, it's a degree 1 factor. And an irreducible quadratic factor, an irreducible quadratic, is of the form ax squared plus bx plus c. That's what we mean by quadratic. And by irreducible, we mean that it cannot be factored. Now, what does that mean when it can't be factored? You don't have to sit and try, because we know that the discriminant b squared minus 4ac, in other words, what's under the radical in the quadratic formula, has to be less than 0. Because to be irreducible means that you don't have any real roots. The graph doesn't cross the x-axis. So what's under the radical is negative, meaning that your two solutions are both complex numbers. So every polynomial can be factored into linear and or irreducible quadratic factors. I would like to say one thing. If you're thinking, oh, I don't know how to do that, neither do I. I can factor a quadratic pretty easily because we can use the quadratic formula. But cubics, well, they're kind of hard. If you Google, you can find a formal algebraic way to find the roots of a cubic, in other words, to factor it. But it's not easy. And in fact, for degree greater than, I believe, 5, it's absolutely impossible. Unless you're lucky, if you guess some roots or you use a computer, but factoring is very, very difficult. In the questions that I'm going to give you, I'll either have it all factored or it will be very, very simple factoring. Here's an example of what we mean. This is a cubic, a third degree polynomial, and notice it is factored into a linear factor 2x minus 1 and x squared plus x plus 1. Now I know that cannot be further factored because b squared minus 4ac, 1 minus 4ac, 4 times 1 times 1, 4, is equal to negative 3, and that's less than 0. So b squared minus 4ac is less than 0. I know I cannot factor it any further. Here's what's going to help us out in integration. Every proper rational function can be written as a sum of other rational functions. Partial fractions, we call them, having as their denominators the irreducible factors or powers thereof of the numerator polynomial. It took me a while to think of how to write that sentence. It's hard to read, I'm sure. But look at these examples. In the first example, we have a degree 1 polynomial over a degree 2, a proper rational function, and the denominator, I just have it factored for you. Notice that, you don't know how I did this, just see. You could check it and cross multiply and add, and you'll see that hopefully it's correct. That this rational function, denominator factored as 2x minus 1 times x plus 5, and it would split into the sum of two partial fractions. We could say smaller rational functions, maybe. That's not really the right word to use, but 1 over 2x minus 1, see, the factor is here, plus 3 over x plus 5. This factor is here. Notice that the numerators of these little partial fractions, the numerator is degree smaller than the denominator. In other words, they're both proper rational functions too. So if you have a linear denominator, on the top you're just going to have a constant. Because this is degree 1, this will have to be degree 0. Look at the second example. We have a degree 2 polynomial divided by, well, notice the leading term would be 2x times x squared, so that would be third degree. This is proper, degree 2 over degree 3. Factored, the denominator factored is 2x minus 1 times the irreducible polynomial x squared plus x plus 1. It's going to split into the sum of two rational functions, both proper. One of them will have denominator 2x minus 1. One of them has this factor as a denominator, and its numerator will have to be degree 0. We know its numerator will just be a constant. Now, the other partial fraction will have denominator x squared plus x plus 1, and notice in this case its numerator is degree 1. We know that its numerator will either be degree 0 or degree 1 because the partial fractions themselves are all proper. And the third example, we have a degree 2 polynomial. In the numerator, the denominator is degree 3. You can see that there, if you squared this, you'd have x squared, and here you have another factor of x, so it would be a cubic. Alright, notice here we have a linear factor, x plus 3, and here it is, x plus 3. And the numerator has to be just a constant. But this denominator, this factor of our denominator, x plus 1 squared, notice, gives us two partial fractions. Because it's squared, it's going to give us the possibility of two partial fractions, one with denominator x minus 1 and one with denominator x minus 1 squared. And each will have degree 0 in the numerator. Even though this, I know this is a little bit confusing, even though this, if we squared it out, would be a second degree, if the denominator comes from a linear factor, the numerator will be a constant. So what we really want to get out of this first video is how do we break these proper rational functions into a sum of partial fractions. You could see that integrating the partial fraction decomposition of a rational function would be much easier, in fact quite easy to integrate, because we just have linear denominators or irreducible quadratics where we can complete the square and do a little u substitution. So here are the steps, and then I'm going to show you one or two examples. First of all, when you're given a rational function, you must make sure that the part that you are going to decompose is proper. So if it isn't, you divide out the polynomial quotient, and then you have plus a remainder over the numerator polynomial that is a proper rational function, like we did at the beginning of this video. Then you factor the denominator polynomial into linear and irreducible quadratic factors. And then I'm going to show you how you set up the partial fraction decomposition and solve for the numerators. So our first example is all factored for us. We see it's degree 1 over degree 2. It is proper and it's all factored. So there's step 1 and step 2. Now, how do we set this up? How do we set up the decomposition? Well, we know that it's going to give rise to a sum of two partial fractions, one with denominator 2x minus 1 and the other with denominator x plus 5. Both of these are linear factors, so we know that their numerators will simply be constants. So there we have set it up, and now we have to solve for a and b. The way I like to do this is first to multiply both sides by, well, it'll be by the denominator, and clear the fractions. So I'm going to multiply by, on the left-hand side, by, well, here, once I'm going to write it in. Normally you don't write all of this. You know how to do this. 2x minus 1 times x plus 5 on this side and on the other side. 2x minus 1 times x plus 5. So as we multiply here, of course, all factors in the denominator cancel, and we have, whoops, I'll keep this in yellow. We have 7x plus 2 is equal to, using our distributive property, we take this and multiply over to this fraction, and we get a times the 2x minus 1 cancels, a times x plus 5. Plus, and similarly, we multiply this to the b over x plus 5. The x plus 5 cancels, and we have 2x minus 1. So that's called clearing the denominators. Well, let's see. There's a couple ways you can do this. The easiest way, I think, by far, is to say to yourself, this equation holds for all x. So I could easily solve for a and b by choosing particular x's that make it easy. For example, if If x is equal to negative 5, then we have a very nice little sentence. We can drop out the a. We have 7 times negative 5 plus 2 is equal to a times 0 plus b times 2 times negative 5 is negative 10 minus 1. Now again, in the future, you do a lot of this in your head. So we have negative 35 plus 2 is negative 33 is equal to minus 11b. So we can solve for b, and we get b is equal to negative 33 over negative 11 is 3. So b is equal to 3. Well, now I could go back up here and plug in b, but I really don't need to because I could just let x be 1/2. And notice what happens. If I let x be 1/2, that's going to be 0. So that term will drop out, and I'll just have, substituting in 1/2, I would have 7/2 plus 2 is equal to a times 1/2 plus 5. Well, instead of adding fractions, I multiply both sides by 2, and I get 7 plus 4 is 11. And multiplying both sides by 2 here, I would have 1 plus 10, or 11a, and I get a is equal to 1. So there is our decomposition. I could go back up here and erase the a and put 1, and the b I put in 3. Here we can just, this will be 1 and b is 3. So we have our results, 7x plus 2 over 2x minus 1 times the quantity x plus 5 is equal to 1 over 2x minus 1 plus 3 over x plus 5. So you see, it would be very easy to integrate the two partial fractions. It's just going to be natural logs. Very simple natural logs. Whereas if we were given the integral of this quantity, we wouldn't know what to do with it. So we're going to factor the denominators, set up partial fractions using the denominators, and then write in what the numerators are, either constants or ax plus b, linear if you have a quadratic denominator, and solve for the constants. This next example is proper. It's a degree 2 over degree 3, and the bottom is factored. So this will give us rise to a possibility of 3 partial fractions. We'll have something with a denominator x plus 3. We'll have a partial fraction with denominator x minus 1, maybe. And, I mean, it's possible that we could get 0 for our numerator, in which case we wouldn't have that in our decomposition. But we might, so we have to set it up as if all these denominators will appear. This is linear, linear, and linear squared. So we will just have constants on the top. I'll write a, b, and c. The only time you have a linear numerator is if your denominator is an irreducible quadratic. So let's clear the denominator, and I'm going to just do this in my head. If you want to write out these multiplications, go ahead. So we have 3x squared plus x plus 8 is equal to, now when I multiply this by x plus 3 times x minus 1 squared, I just have a times x minus 1 squared. The denominators are all going to cancel. Then I have b, and I have x plus 3 times x minus 1. One factor of x minus 1 canceled. And on the last one, 2 factors of x minus 1 cancel, and I have c times x plus 3. So now I'm going to pick some very convenient values of x because this sentence is true for all x. Why not let x be 1? If x is equal to 1, we get, well, plug in x equals 1. 3 plus 1 is 4, plus 8 is 12, is equal to, oh, when x is equal to 1, this is gone. It's 0. And I just get, ooh, and so is this. When x is equal to 1, this is also cancels out, is 0. And I just have c times 1 plus 3 is 4. So that gives me c is 3. So we solve for 3, and maybe I'll just go up and cross out the c and put 3. Well, what else could we let be? X be. Let's let x be minus 3. If x is equal to minus 3, then plugging in minus 3, I have 3 times 3 is 9 times 3 is 27, plus 3 plus 8 is plus 11, is equal to, x is negative 3, so it's going to be a times negative 3 minus 1 is negative 4 squared is 16, plus negative 3, this will all be gone, it will be 0, and so will this. So it just gives us, this tells us that 38 is equal to 16a. Did you catch my mistake? I knew that it didn't turn out to be a fraction here, so I went back and checked, and look, I plugged in negative 3 into this, and I got negative 3, so I have 27 minus 3 plus 8, so this would be plus 5. I'm sorry. Arithmetic error. And 16, so that means that 32 is equal to 16a, which gives us conveniently a is equal to 2. I knew I made up all these problems to have nice results, and so let's cross out a and make it 2. But this, be very careful, because it's easy to make an arithmetic mistake, and maybe you're better to write more stuff out than I do. Well, I don't have any other convenient value to make x equal to. I mean, nothing that's just going to wipe everything out. So why don't we just pick one that's easy to plug in? Let's let x be 0. And let's use our values for what we know. A is equal to 2, so I'm going to just write 2 there. And we know that c is equal to 3. So this last step, I'm just going to plug 0 in. Well, it's easy. On the left-hand side, I just get 8 is equal to 2 times negative 1 squared is 1, plus b, that's what we're hoping to find, and we have 3 times negative 1 is negative 3, letting x be 0, plus 3 times 3 is 9. So this gives us, what? 3b, moving that over to the left, is equal to 11 minus 8. So that gives us 3b is equal to 3. That's nice. So b is equal to 1. And there is our partial fraction decomposition. 2 over x plus 3 plus 1 over x minus 1 plus 3 over the quantity x minus 1 squared. And look how easy those would be to integrate if that was our problem. We'd have a natural log and a natural log, and then we would use the power rule for the third one. This is the last example. I wanted to do one where we have an irreducible quadratic. We have a proper rational function. The denominator is factored, and we know then that we will set up a partial fraction with linear numerator 2x minus 1, therefore a constant denominator, and we will have a denominator x squared plus x plus 1, which is an irreducible quadratic, and so I will put bx plus c. That doesn't mean that the numerator will necessarily be linear. b could be 0, in which case we just have a constant. But you have to allow for having a degree 1 numerator. So let's clear fractions, and we get 9x squared plus 9x plus 2 is equal to a, the factor of 2x minus 1 cancels, and we have a times the quantity x squared plus x plus 1, plus, now we have bx plus c, the quantity, times the linear factor 2x minus 1. Now we plug in some convenient values. Well, the only real convenient one I see is the one that will make 2x minus 1 equal to 0. So x equals a half. X is equal to a half. That will wipe out the whole second term here. But we do have some fractions. 9 times 1 half squared, 9/4, plus 9 times a half, 9 halves, plus 2 is equal to a times, plugging in a half, we have 1/4 plus a half plus 1. And this is just going to be wiped out. That's 0 because we're letting x be 1/2. This implies that 35/4 is equal to 7/4 a, which gives us 35/7 is equal to a, or a is equal to 5. So I can go up here and put 5. And I can go right here and put 5. I'm going to need it. This is a little more complicated than just having two linear factors. So I'm going to use the fact that a is equal to 5. Alright, so now I want to think of another value of x. Well, if I let x be 0, I would make this term disappear. And I know a is 5, so let's let x be 0 and see what happens. If x is equal to 0, then plugging in 0 on the left, I just have 2, is equal to, plugging in 0 here, I have 1 times 5 is 5, and then I have plus c. bx plus c is just c, and my factor here is 2 times 0 minus 1 is just negative 1. So this gives me c equal to 3, right? Yes, so c is equal to 3. So let's go up and cross out our c and make it equal to 3. And I'm going to put 3 here. We have to use it. Now I still have to solve for b, so I've got to take, there's nothing that will give it to me for free. So I have to let x be something. Well, let's pick something easy to plug in. How about x equals 1? If x is equal to 1, plugging it in on the left, I get 9 plus 9 is 18, 20 is equal to, and then I have 5 times 1 plus 1 plus 1 is 3, plus b times 1 is b plus 3. Be careful, it's b plus 3 the quantity, times 2 times 1 minus 1 is just 1. So this will give us, 20 equals 15, so 5 is equal to b plus 3. So b is equal to 2. And we're done. So b is equal to 2. And we have that this rational function is equal to, in its partial fraction decomposition, 5 over the linear factor 2x minus 1 plus 2x plus 3 over x squared plus x plus 1.